welcome to a summer edition of Foresight's Space Group. We had a really exciting workshop and we were currently working on all the recordings to be published as soon as possible. But in the meantime, we're going to continue our virtual seminars. And I'm really delighted to have both Kieran and Brad here. And I think we already discussed offline just how long both of you have been involved with Foresight. And so that's been really wonderful to hear, certainly longer than I have been. And yeah, I'm super, super excited to have both of you on here. And Brad, you've been working on really interesting concepts and theories. And I'm really happy that you picked us as a venue to share them in. Kieran, do you want to say a few words before we kick off Brad?
Yeah, briefly, I think Foresight is older than you, isn't it, Alison?
It is. It is older by 5 years than I am.
Yeah.
Okay, well, and Brad and I are older by 5 years as well.
Barely.
Brad, welcome back. It's been a while. I know you and I used to, hey, Lydia, you and I used to talk semi-regularly. I miss those days. So let's start that again. But for now, why don't you take it away and tell us this thing that you've been thinking about for so long?
Well, we've had a few presentations in the Foresight Space Group about people trying to address Fermi's paradox. We've had Robin Hanson. We've had a little bit at one of our formal meetings, Eric Drexler and Anders Sandberg and a few others also presented some really interesting things. Now, let me change my own window because I want to see you, not me. And so there's been a lot of fascination with this question. Of course, it's a very big and deep question, not about what's happening in low Earth orbit or the other things or the solar system, as we'll typically be talking about. But of course, the big question that Enrico Fermi asked, I trying to remember how long ago it was. And okay, that is the wrong button to push. And I guess my computer has turned off. Hold on, let me just tweak it. I have these little macros that make sure that everything remains in the right focus. And they have hidden themselves. As I say, AI is easy. It's AV that's hard. Okay. Fermi asked, supposedly at a lunch in Chicago, this was, of course, before they thought to call it Fermilab, that since a lot of people were concluding that there should be a lot of intelligent life in the universe, it seemed very unlikely that the human race was unique, but obviously we don't see any evidence of them. And he thought that was a paradox. How can life be common in the universe and yet not visible to us? And so apparently at lunch, he just sat down and said, where is everybody? Or where the hell is everybody? Now, this is actually because of something I call the anti-Copernican heresy, which has recently become a little popular, actually, among Robin Hanson, a few others. Copernicus, of course, was a heretic because he suggested that the Earth was not the most special and unique planet in the universe, that it wasn't the center of the universe. And that was, of course, wrong, or Copernicus was right. And we've instead taken as doctrine now that the Earth is ordinary, or at least not tremendously unusual. And in fact, to suggest that the Earth is the first planet or only planet with intelligent life at least in our light cone, is now a heresy of its own. It's refuting Copernicus because, frankly, every time we've sided with Copernicus, we've generally been right. And every time we've followed the old rule, we've generally been wrong. But there's been a temptation because of the Fermi paradox. Many people have been driven to the conclusion that we might actually be the first. And I'm not a fan of that. And so I'm always on the lookout for ways to help counter and explain the thesis that's going forward. And we saw Robin Hanson's grabby alien thesis in this room and a few others who were, again, trying to say that, yes, indeed, we were the first in our light cone. Now, many of you will have seen the sort of model created by the Russian astronomer Kardashev about what he thought civilizations might be in the universe in terms of how much energy they used. Did they use the energy of their planet? Did they use the energy of their star? Could they use all the energy of an entire galaxy? He called those types 1, 2, and 3, to suggesting very large steps between those levels, but that in particular, those of type 3 and even those of type 2 ought to be visible to us. Those of type 2 would probably be building, people theorize, something to capture all the energy of their star. Freeman Dyson was one of the first to suggest this. It's named after him, the Dyson sphere, although frankly, it's hardly the most significant thing that Freeman did, but probably the most famous thing in some ways. The idea of building some kind of structure which can capture all the energy of a star, and that would be the ultimate of the type 2 civilizations. And so some people said, well, if there is life out in the universe and it is advanced, it would eventually do this. And we would notice it if it happened in any volume, because if you were to enclose your star in a shell and capture its usable energy, the result is you would not emit no energy, but you would emit much less energy, and it would be much redder. It would have much higher entropy. You'd be extracting all the useful energy or negative entropy from the star, and we'd see this. We'd see any interstellar civilization that began on one planet and colonized out, limited by, as far as we know, the speed of light. We would see a growing sphere or an already grown sphere of these Dyson spheres, and it would be red. And so people like Eric Drexler, founder of this organization, went on searches for this sort of bite out of a galaxy. Somewhere in the universe, there would be a galaxy in the process of being eaten by intelligent life, some sort of evidence of their engineering. He and others who searched could find none. And so either they don't make Dyson spheres, maybe the speed of light isn't a limit, or maybe there's something else fundamentally wrong with those assumptions, or, as some have concluded, maybe we're the first, and that's why we don't see anyone consuming the universe. Well, again, that is the anti-Copernican heresy. So I'm going to define a few things for you. And first, I'm going to tell you that what I'm defining intelligent life as is something very simple. An intelligent species basically turns usable energy, negative entropy if you prefer, into thought. That's sort of a very broad definition of what intelligence does. It takes the energy and thinks. And that could be anything. We're an example of that. We do it in a pretty inefficient way, as I'm going to tell you, but that's what we're looking for in the universe. And I'm going to give you some assumptions that I have made and that many other people make in trying to analyze this question. First is, these are not proven assumptions, but that physics is finite. There isn't an infinite amount of physics to learn, that you can, at some point, if you're smart enough, learn all or most of the physics and understand it. You may not fully understand things, and your learning may include things like the Heisenberg uncertainty principle that say there are things that are unknowable, but nonetheless, that an intelligent race, after a short amount of time, cosmically short amount of time, would come to understand physics to some degree. Now, we humans, on the other hand, are the stupidest race in the universe because we just got technology yesterday. We just got technology a minute ago on the cosmic scale. And so among the technological civilizations, thinking civilizations of the universe, we have got to be very close to, if not the most primitive. Everyone else knows more than we do. We also are assuming, and this is a common assumption in any kind of analysis of Fermi's paradox, is that there are species out there that want to thrive and expand. Now, we have an existence proof. The only intelligent species we know about, humanity, is a growing intelligent species that wants to expand its number and its territory. And not all species will be of that type. Robin, in his work, talks about quiet and loud aliens, but we know of at least one. The only one we know of is of this type. And so it seems like a reasonable assumption that there would be others out there. A new assumption that I am making, I mean, I'm not the first to make this, but it's pretty important to what I'm going to talk about, is that the winner also seeks to be efficient. That optimizing your efficiency gives you more thought for a unit of energy. If your goal as an intelligent species is to turn energy into thought, and you also like to grow your number and expand what you do, you naturally want to be good at turning energy into thought, which means you want to be efficient. You want to optimize your processes. Evolution naturally creates life forms that optimize, because in the competition between evolutionary lines, this happens. So again, we have an example of this on the Earth. Now, this may not be a universal principle, but if you have a battle or competition between creatures that are more efficient and more optimal, can do more with their resources, it is likely that the more efficient creatures will be the ones to win. Now, one exception to this rule of being efficient would be conflict, war. In war, you will waste energy in order because victory becomes more important than efficiency, because victory is your survival in war. So one exception, but generally, if you're not in war with someone else and you are interested in growing your number, you're going to want to be as efficient as you can. Now, so far, it seems that when it comes to thinking, that artificial should be the most efficient. That's not true on Earth right now, actually. We still haven't managed to make thinking machines that are anywhere near and as efficient as human brains in terms of taking 30 watts of energy and doing the amount of thinking that the human brain does. But that by and large, when we try and build systems, the artificial systems also tend to be the most efficient. But here's an interesting attribute of efficiency. Efficiency is dark. Efficiency does not waste energy. It does not send out additional energy out into space. It tries to use it all and send out the least it can, or send it out the reddest it can. Now, if you can see something, that means it's not efficient. If you can see stars are, it turns out, incredibly wasteful. They basically just are burning up their fuel, and as far as we can tell, most of them doing absolutely nothing with it. Even our own star, almost all of its energy is simply cast out into space. It's not efficient at all. But most of the universe is dark. So we're reminded of a very famous old joke that I'm sure you've all heard, that the guy comes across a guy looking under a street lamp for his keys, and he says, or his wallet in this cartoon, and the guy passing by says, "Oh, well, did you lose your wallet here?" I said, "No, I lost it in the park, but this is where the light is." And this is a parody of the activity of scientists, that we tend to do this. We look where the light is because we don't know how to look in where the dark is, even if the answer is in the dark. But to be the dominant party is to be the efficient party, and to be efficient is to be dark, that means that by definition, the dominant alien intelligences in the universe will be invisible to us, or nearly invisible to us, or invisible to people at our level of technology, because again, we're the stupidest people in the universe. And as a result, it's unlikely you're going to see them. But there's more to this darkness than just the idea of not having light there. As the common model in physics, all this is disputed, suggests that most of the universe is what we call dark matter and dark energy. Certainly, dark energy is a lot more speculative and really very theoretical and hypothetical at this point. Even some people feel that dark matter is hypothetical, although there is some decent evidence for it. But this part is commonly accepted in physics, that of the matter in the universe, about 1/6 of it is baryonic matter. That's us. Baryonic matter, protons, neutrons, all the things that are us and make up us, and the stars, and everything we see is this. And that the other 6/7 or so, or whatever it is dark matter. By the way, in addition, among the baryonic matter, which is mostly hydrogen, only a fraction of that is in stars. A lot of it is out there in interstellar gas and dust, and even in intergalactic gas and dust, and not visible to us. So the stars are a very tiny part of the matter in the universe, and if dark energy is something, they're a very tiny part of the total material or usable energy, again, what dark energy is, we don't know, in the universe. So we're focusing all of our attention on what we can see, namely stars and things around stars. And so we're focusing our attention on a minuscule fraction of the universe in our search for intelligent life. And so as we've concluded, we can't find it, but we've concluded that when we're looking at a tiny part of it. Now, let's also look at all the energy that powers us here in our bodies today. All the energy we've ever known, seen, everything we've ever done, every thought we've ever had, has come from hydrogen fusion, which is to say, stars with their gravity pack hydrogen down into small spaces. Bang, they hit each other occasionally fast enough to fuse, and we get 4 hydrogens, which eventually fuse to become a helium, and we spit off a couple of gamma rays and a positron, which are turned into heat in the star that boils up from the bottom of the star, eventually reaches the surface, and this black body radiation is re-emitted as photons at, in our case of our sun, at about 5,000 degrees, other stars at other temperatures. That's everything we know. That's everything we've ever seen, understood, is that process. Well, that process only extracts about 1/150th of the energy in the hydrogen, which is in the stars. And the stars are only 0.4% of the material in the universe. So everything we've ever seen or looked at is 1/150th of 1/200th of what's out there. We are looking at the tiniest fraction because it's the part that's us, that we live in. We have this natural bias and tendency to do. So let me tell you about some of the ideas that happen in the discussion of Fermi paradox that I think lead us to mistakes. First of all, we imagine that, as I've just said, that we could see these smart, efficient beings. It seems unlikely when we're looking at such tiny thing that we would see them just because we're so primitive. Maybe when we get more advanced, we'd be able to see them. But as if you studied radio technology here on the Earth, today for our radios, we use frequency hopping, spread spectrum, ultra wideband communications, which would have looked like noise to the radio engineers in my lifetime, in one human lifetime. Quite. I mean, actually, it's famously known that Hedy Lamarr, the movie actress, was one of the people who pioneered the idea of frequency hopping. But so it was done in very primitive ways in World War II. But nonetheless, our old selves couldn't see our current selves. And the idea that we would see these smarter races seems unlikely. Another concept that is basically the hubris behind almost all SETI that involves listening for radio signals or looking for optical signals is this concept that the aliens don't know about us, right? That we're waiting for them to discover us. That's the reason we're not hearing from them, is because we're waiting for them to contact us. But the truth is, they've known about us for longer than we've known about us. The reason is that they don't have to travel very fast to explore the universe. We, puny humans, again, the stupidest race in the galaxy, we're now able to look at planets around other stars, going out for not that far yet, but we're getting better and better at it. But with our meager skills, we're able to examine the atmospheric composition of a few planets around other stars and detect them. We can do that. They can do much better. They have known for quite some time that this planet has free oxygen in its atmosphere, which it started having, I think, around 150 million years ago. I'm trying to remember when. I don't remember the exact date. I wasn't there. But we've had this free oxygen doesn't sit on its own. You need a process to regenerate free oxygen, of which life is the process on the Earth for that. It's not necessarily the only process. But we're already have been for 100 million years, obviously something unusual. And a few million years ago, it became clear that there was more complex biological, weird chemistries going on this planet. And any alien race that's interested in looking for others would have noticed us some time ago, would have sent a probe at 100th of the speed of light, and it would have gotten here long ago and been sitting on the moon or somewhere else. And a lot of science fiction that's made this speculation. But the idea that they just are trying to talk to us and we can't hear them is silly. They know we're here, and if they want to talk to us, they have the means to talk to us. Because again, we're the stupid ones. They're much smarter than us. The idea that they could not figure out how to make a signal, well, that's pretty obvious from the fact that we humans, again, with barely any technology, we've sent a space probe out, Voyager 1 and 2. We've sent them out outside of the heliopause of our star. If we wanted to spend the money, this is a question of money rather than technology today, we could put a space probe out 1/10 of a light year from the Earth, take a few years to get out there, but we could put it out there. We could put a laser on it and a nuclear reactor, and we could have it send laser pulses at any star that we wished to send a signal to. These laser pulses would be visible to the naked eye of a creature like us, or at least with a telescope, because it depends how far away you are to get the angular separation from the sun. But the point is, even we could make the sky blink for other aliens if we wanted to spend the money. We don't want to spend the money, but we could. And they, again, they're not the stupidest race in the universe. They, if they wanted to be signaling us, could be putting drone shows up in our sky that we could see with our eyes if we wanted to. So the idea that there's going to be subtle signals out there that we just have to listen carefully enough and do enough signal noise decoding on, that's not going to work. What might work is finding their deliberate waste, like their radar. Some of the SETI people are looking for that. So that's not where we're going to find them either. And so they could say hi if they felt to. They obviously either don't exist, which is that anti-Copernican heresy, or they don't want to talk to us, at least not yet. That's depressing, but it's the conclusion that I've come to. All right. So now let's get to the question of, if aliens are dark, if they're in dark matter, what does that mean? And I can't say a lot about what it means because we know very little about dark matter, and we even debate whether it's real or not. But even with our primitive knowledge, we have some ideas of what may happen. Now, it's, again, this is going to be very speculative because it involves things far beyond what we're able to do. But it's just exploration to say it's possible. Now, this diagram in the background of this slide was made by my friend Adam Brown, and Adam has also presented here at the Foresight meetings. And he did a paper a couple of years ago where he showed how an advanced civilization could extract all the energy from dark matter. They could do this if they had super strong materials by lowering the dark matter towards the event horizon of a black hole, where it would then be destroyed and turned into energy, and you could capture that energy if you were capturing the energy coming out of that black hole. And we do this? Of course not. We don't have anywhere near the technology to do that today. But it's an example of the theoretical possibility of extracting efficiently the energy from dark matter. And again, an intelligent race. Now, I should point out, and some people have mentioned this, I am not suggesting that the dark aliens are necessarily made of dark matter or that they evolved within dark matter. It seems more likely, in fact, that they would have evolved as we did in the baryonic matter, but then later advanced and expanded their knowledge of physics to the point where they realized most of the energy out there is in the dark matter. We should be making use of that. Why are we dicking around with all this tiny fraction of the universe that is stars and the energy from stars? We should be out there doing it. And so they could just be beings. Let's face it, my most likely conclusion is that they would be artificial, computer's the wrong term, but artificial computation beings who run themselves and power themselves on the energy they can get from dark matter. Another way you can get energy from dark matter is if you can find the dark matter antiparticle, and our standard model demands that every particle has an antiparticle, and if you can get those particles to hit each other just exactly, dark matter is hard to manipulate. Gravity is the only thing we know that acts upon it, any force we know that acts upon it. But if you could collide dark matter and anti-dark matter, you would be able to extract its energy completely. You'd get 100% efficient E equals mc squared extraction. As I mentioned, hydrogen fusion gets only 150th of the E equals mc squared total energy embodied in those protons in the hydrogen. So while they could be made of dark matter, and we have no understanding of the physics of dark matter, they don't have to be. They just have to be beings who are extracting energy from dark matter as their fuel. And I'll go into why they would do that. It's interesting to note, by the way, that one of the biggest pieces of evidence for dark matter is that there are galaxies that do not have dark matter. Dark matter was hypothesized and then demonstrated by the fact that galaxies rotate in a way which implies that their mass is much larger than the visible mass of the stars we see. And so it was hypothesized there must be invisible mass in these stars, or that our model of gravity is wrong, which is the other explanation that people put forward from time to time, although they haven't yet been able to get scientific consensus behind it. So the existence of stars without dark matter, of course, if real, is proof. So these stars, for example, like the one in this image, they do not lens the way that a star with dark matter, or galaxy, with dark matter would do. One very speculative suggestion one could make is possibly some creature ate up all the dark matter in this galaxy and is on its way at the speed of light to eat another galaxy. So remember I said that people looking for intelligent life said they predicted they would find galaxies being eaten or having been eaten. And maybe I'm saying we could be looking at one here. Although if this is true, there are not very many of these. Most galaxies are chock full of dark matter. And so this would imply that the arrival of such civilizations was relatively recent. The same arguments that suggest that humanity might be the first intelligent race in our light cone, however, are strong arguments for the fact that other alien intelligence would also be relatively recent, just not as recent as we are. We're super recent, and they would be billion years old, or a few, or tens, hundreds of millions of years old. So I'm not going to put this forward as a case I put a lot of weight behind, but it is an interesting observation. By the way, this model now suggests we need to expand what Kardashev wrote about. Remember, we talked about the type 1, type 2, and type 3 civilizations using the energy of planet, star, and galaxy. Well, now we would like to add a whole extra several layers on top of that. So Kardashev talked about the energy that comes from gravity-triggered hydrogen fusion. That's what stars and galaxies put out as their energy in Kardashev's model. But there are higher levels that could come. There could be where you're controlling the fusion and extracting more than 150th from it. You could be looking at getting all the mc squared energy out of the baryonic matter in your planet, star, or galaxy. You could be getting all the mc squared energy from all of the matter, including the dark matter, and that's what I've been talking about as the likely home of the aliens. And then you could look at levels beyond that where you're somehow able to use dark energy, whatever it is. Then the ability to use physics that's just unknown to us, and I would even count dark energy in the class of physics unknown to us, but at least we postulate it. And then finally, the top level of this would be the species which is able to make use of all the energy that all physics allows. So there's quite a lot more in terms of levels of civilization that could exist beyond what Kardashev originally proposed. And so lots more room to look for things. The biggest question that's come forward when I broached these ideas with Robin Hanson, he asked this, and I had already asked it myself as the biggest question. So let's say that stars only account for 1/1800th of the interesting energy in the universe, as I've calculated. But why would they leave even that 1/1800th alone? Why aren't they also eating the stars as well as living off the dark matter in there? This is not something that I believe I have a really great answer to. This is one of the more difficult questions in postulating this model. However, there are some ideas which point in this direction. One of which, this is a picture of a quantum computer, experimental quantum computer. And if you've looked at these, you know that they're all sitting around trying to get themselves down to fractional Kelvin temperatures, because lots of great things happen when you're cold. And in general, thermodynamics tells us that the colder you are, the colder your environment, the more efficient all your processes are, the better you can turn energy into useful thought or work, the colder you are. So stars are wastefully hot. They're terrible boiling things. They're terrible, horrible places to go if you're the sort of creature who is interested in top efficiency and cold. Stars are burning themselves out, and over the next several billions of years, they will burn themselves all out, in fact. They will use up that 1/150th of the energy, most of them will turn into brown dwarfs, and eventually cool off. And as such, you can wait to get the energy from them in a really useful way when you're cold. You don't want to go down into these hot places. So that's one possibility. Another possibility, which has been proposed in Fermi's paradox a lot, is called the prime directive or zoo hypothesis, is that we're a nature preserve. Well, again, the only species we know of, the humans, we make nature preserves. So we have one existence example. There exists at least one species which makes nature preserves, and at a certain point in its maturity decides it wants to leave things untouched. And so if you're talking about only 1/1800th of the energy in your civilization, you might decide that's within the nature preserve budget. Let's leave the other stars burning as they are. We'll burn them up. We'll use them up later when they're brown. And we'll let other civilizations arise, which may become interesting. We won't let them take over the universe. We're here. We're probably not going to let them take over the dark matter. Maybe when they get to the point where they might even be able to do that, we might start talking to them and welcome into our civilization, or we might crush them and kill them. Who knows? There's been fictional speculation of all of those possible alternatives. But again, we have one existence proof. It doesn't guarantee that it would always be done. It's actually only necessary to some degree that the species in our areas are the ones that leave the nature preserve of us, although we should see other galaxies being eaten, as other people postulated, if this is not the case. So this actually suggests that you have to have a civilization that is older, not a young one like in that galaxy empty of dark matter, that is older, that rules our light cone and sets the rules for it, including having the nature preserve. But dark matter has this wonderful attribute, and it's why I think they would love it, which is it doesn't clump. As people started theorizing models of dark matter, they came up with the idea that it doesn't interact with baryonic matter, and it doesn't even interact with dark matter other than through gravity. And this is the sort of common model of dark matter today. And because of that, it doesn't form stars. I mean, it forms sort of star-ish things. There's been some talk about this recently, actually. But the point is they don't come together and physically hit each other, which is what causes fusion. Stars burn up because regular matter collides to itself through van der Waals forces and other things hard enough that it can fuse, and that starts the star, gets the star lit and starts the energy usage going. With dark matter, stars don't light up. And that's great, right? I mean, that's a bug. That stars are a bug, not a feature, as far as creatures trying to access all the energy in the universe, because stars burn themselves up without you being there, without you using it. Dark matter won't offer its energy up unless you actually want it then, which is a much more controllable process, a much nicer process. That means as well that the dark matter universe won't suffer a heat death the way the baryonic matter universe will suffer. While the heat death of the universe is probably not a personal concern of most of us, except for those who are very into life extension, it is an eventual end for what we have here. The thermodynamic processes will run out, the entropy will increase, and we'll no longer be able to get energy from the stars. Many giga-years from now, but nonetheless, if you're a very long-lived species, that's less giga-years than you want to be around. But dark matter doesn't have that problem. It doesn't get a heat death. The only thing that would use up the dark matter in some particular way would be if the inflationary cosmology model is correct, and the universe is going to expand and everything is going to get so far from everything else that you can no longer do anything or have any interactions. And that's if the cosmological constant is too high. Of course, as we try and measure the cosmological constant, we keep seeing it being very close to 1. We don't really know what it is. But there are some models where the universe just expands into nothingness and time ends as far as you're concerned in being an intelligent being. However, absent that, you actually have this interesting conundrum because you've got no limit on the amount of time that you can use it. You just decide, how fast do I want to use up my energy to do what I want? And there's this much energy in the universe, and I use it up at this rate, and that's your definition of how long time is. That gives you a rather amazing ability, which is you can pick your clock. You can decide how fast you run, especially if you're any kind of informational being. We humans can't pick our clock, but more advanced beings could pick their clock. And there's an argument that you would pick your clock to be very slow. Now, if your time is infinite, there's, again, no cap on what you would do. You would pick the optimal time so you can get the most efficient operations, the most life out of the resources that you have. And this gives you a rather unusual ability that's foreign to us humans, the ability to change the speed of light. Now, the speed of light is, of course, a constant of the universe, but it's expressed in a distance per second, 300,000 kilometers per second. But if you can change your clock, you can change the second, your subjective unit of time, which is what the second is. So if you make the second longer, if you make how long it is for you to perceive a second longer, light travels faster. If you run yourself 186,000 times slower than we do, then, or 300, whatever it is, then the speed of light light years take seconds to you. And so therefore, suddenly you're in a universe where you can travel between concentrations of matter in reasonable times. You could go to Alpha Centauri for lunch if, for you and everyone else, agreed that 4 years should take place in just a few seconds. Well, that is something that's very interesting. It also means that if you're a computational being, your computation and size are limited by how long it takes signals to get from one side of you to the other side of you at the speed of light. We already see this a little bit in our computer chips. We're starting to see light delays famously, if you ever looked at the Cray 1, Seymour Cray would deliberately make the wires between the chips in the 1 nanosecond long if he wanted a nanosecond timing delay. So if you can control that, you can make yourself bigger and thus more capable and able to do more thought, because you now, again, you've increased the speed of light from a subjective standpoint. So that's Anders Sandberg actually wrote a paper. In fact, he stole a number of my ideas before I wrote them, which was quite rude. I recommend you read his paper because he explores some of these ideas in other ways. But he has also suggested that the other motive of these beings is similar to what I briefly mentioned earlier, that they would like to wait for a colder universe so that they can be more efficient. The universe in general is just too hot, even out in the dark between the stars. It's still too hot, all of these annoying galaxies sending radiation at you, ruining your efficiency, so that the wise thing for them to do might be just wait for that. Wait enough giga-years for a nice cold universe and then live your existence. And that's another reason why we're very unlikely to see them with any technology roughly similar to ours. So they don't want to talk to us, so these little photos of the aliens are pretty unlikely to be actual aliens. We're too hot, we're boring because we're stupid, and we're also running way too fast. We're mayflies as far as they're concerned. We're beyond mayflies as far as they're concerned. So that's the basic summary of the concepts. Let's get into discussion, challenges and flaws, and see if where you think the aliens are. Because, of course, the disappointing thing about what I've just said is that we're not going to talk to them. We're very unlikely to talk to them in any of our natural lifetimes. We might not even talk to them in the life extension expanded lifetimes that some people in Foresight are hoping for, particularly if Anders is right and they're waiting for the universe to get cold before the real action begins among them. So the main point, though, is that our idea that we will find them by looking at stars because we live on stars is horribly anthropocentric. And unfortunately, that's a pessimistic view on how likely SETI is to succeed. Thanks very much.
Thank you,
Yes,
Brad.
thanks. Turn on your cameras.
Thank you very
Right.
much. Hey, so I'm gonna start off with some questions that I've been accumulating during this talk here. And I guess what I'd like to start with is
You could unspotlight me, by the way, I think, if you want, if you did spotlight me.
I
Go
would
ahead,
like
Priyan.
to start with the question of outliers. When a lot of these arguments are made, there's at least an implicit statistical component, and that's fine, except outliers like Grabbies or Borgs or various sorts of things, I suppose, can alter the landscape, even if they are unlikely. Do you have anything to say about that?
Well, yes. I mean, it's the flaw of, and there are people who've collected books of Fermi paradox answers. And the flaw of most of them is they do make a supposition that has to be true for every race ever on every planet and every star and every galaxy in the universe. Like people who say maybe there's a great filter that, or like every race destroys itself in a nuclear war. That's an answer that some people will give to Fermi. But then that has to be true for every possible race, including ones that are very different from us. And it doesn't seem like a very good thing. So yes, they've got to be outliers. So this model has, I wouldn't say I think it's a complete answer to that question in any way, but the model that a small number of civilizations in the early history of the universe learned enough physics to exploit dark matter and moved their substrate into dark matter, and they now own and control the whole universe. And they're keeping the rest as a nature preserve. And so all the varieties now, there could be just one such civilization in our light code, or there could be multiple who met and either joined or destroyed each other. But one way or another, yes, all of those, possibly just one, have decided that why waste your time with 1/1800th of the universe when 1799 1800ths of it is there for you to exploit. And that is something which is universally attractive. If you knew how to do that, if you knew how to get access to the rest of the universe, it seems unlikely you would spend your time in the tiny fraction, even if you were born there. I mean, you might do some stuff there, but not necessarily visible stuff. Now, Ed Robin argues that no, there'd be somebody who'd say, no, I still want to build Dyson spheres and take that little bit of energy, and so we should see it. And I don't have a guaranteed answer to that. I mean, I think it is a valid question. However, I present a possible model where the masters of the universe are the ones who are dealing with the real stuff, and they are not allowing that to happen in the baryonic matter. And Creon vanished. I don't know if I mean, we have a small enough group that I don't even know we have to do hands, but you may also unmute yourself and just go in. And I see there's a little bit in the chat. I will open it up. I didn't have it while I was talking.
Yeah, why don't we start with Micah?
Could the explanation of that potentially be that when you're civilizations that are capable of building Dyson spheres and stuff like that are sufficiently close to discovering the dark matter stuff and therefore are extinguished as potential competition, like that? Perhaps that's close enough that that's where you turn the nature preserve from a nature preserved into extermination.
I mean, I think that's right. And again, we only have our example to look at, and it is a flawed argument to assume everything is going to be like us. But we're accumulating physics pretty fast. We went from pre-Isaac Newton to now in 5 centuries. And in 5 centuries, you can only go 500 light years, and that's only if you travel at the speed of light. So if that's evidence of how quickly physics can be learned, it does seem likely that a civilization would start getting more and more physics. I mean, we're hoping that we're going to get a real complete model. We keep running into things like dark matter, which tell us, oh shit, our model is missing some very important stuff. But nonetheless, we're of the belief that in a cosmic eye blink, one moves from no physics to the physics we have. And if the full scope of physics is 1,000 times bigger than ours, and maybe it takes millennia for intelligent beings to do it, but quite probably not.
We have also a question from Jay, who mentioned in the chat here.
So why would you always choose to wait? Yeah. Well, if you don't wait, somebody else takes over your territory. That's one reason.
Yeah, and you already answered that with the principle that you can't have a solution that requires everybody to have the exact same culture. There has to be a solution that would, for some reason, that's why everyone ends up doing that. Or the first one, I guess the first one decides. So if you have the very first one takes over the universe, then what if they decide we're going to have 99% be nature preserve and anybody else that pops up won't be allowed to do that? Then it doesn't matter what the other cultures are. The first culture chooses for everyone.
But I did say something else, which is that I believe there is I don't know what kind of law you want to call it, because it's not a physical law, but evolution seems to tell us that that efficiency is universal.
Yeah, efficiency is hard to, if there's anything competing, then the most efficient one will come out ahead.
But also, even if someone's not competing with you directly, but you're intelligent enough to imagine competition, you also seek to be more efficient.
We don't see that.
We don't?
No. If you look at large organizations like the Soviet Union or the US government or the EU, once you get big enough, efficiency becomes less and less interesting.
So sorry, I will agree with you about that, but I believe that's a shorter term phenomenon in the sense of, but we don't have any examples in history of civilizations that stagnated for thousands of years and didn't increase their efficiency over thousands of years. So it's a hard question to answer. I do get your point though. However, what I'm looking at is that if you're an intelligent species and you're looking, and you are, and I've said, we're looking at, like humans and like almost all life on Earth, a species that wants to grow because we've been evolutionary programmed to like to expand and grow. Once you start thinking about that consciously, you say, we want to grow, we have finite resources. Now, right now on Earth, we don't have finite resources. We only have captured a tiny fraction of the resources. So our normal way of growing is get more resources. But once you get to the level that you've mastered physics and you've mapped the energy available in the universe, and so you say, okay, here's this finite pool of resources, and here's us. And I could be one being that just wants to run myself for as long as possible. I could be a multi-being civilization that wants to have more offspring, because that's, again, what evolution has programmed into everything that comes from evolution. We might consciously undo that, but for now, that's how we are. You would just rationally sit there and think and say, I need to be more efficient, or I will live less, or I will have fewer offspring. As soon as I'm in competition with anybody, it becomes forced on you to do that. But I'm saying it could even happen when you're not in competition because of that rational argument.
Yeah, I like it.
Wait, we have audience questions. Should we get to them?
We're doing them,
we have one from Ron. Yeah, Ron, go for it.
I have to unmute myself and lower my hand so that I don't get redundant here. Okay, great. Enjoyed your talk. It was very interesting. I spent most of this week at the Interstellar Symposium in Montreal, which was sponsored by the Interstellar Research Group, which formerly was the Tennessee Valley Research Group, in case any of you are familiar with that lineage of organization. And they actually host one of the more credible interstellar conferences that one can tend to go to amongst the landscape of interstellar conferences that are offered out there. And of course, every time this group gets together, the Fermi paradoxes is either discussed on the side or actually on the agenda. And it came up twice on the agenda this week. One of them was Lee Pascal, who argued. Well, let me circle back to Lee, because Lee was Lee Pascal. He was sort of a point solution to the problem, where a broader talk was, let me get back to my agenda so I get this exactly right, it was presented by someone who's written a series of books, initial book, and then an update on solutions to the Fermi paradox. It was Stephen Webb, and he's done a couple of books, one about a decade ago or more than a decade ago, and then it was revised again, something else. His original one was entitled 50 Reasons 50 possible solutions to the Fermi paradox.
I might have read that book.
Yeah, when it was reissued a decade or so later, it had gotten up to 75 possible solutions to the Fermi paradox. And he made the open offer, if anybody had one that was not already in his book, he was interested in getting it, but he was not interested in a third revision entitled 100 Solutions to the Fermi Paradox.
You know, what he wants is the one revision called One Solution to the Fermi Paradox.
Well, sure. Well, but the real point of what I wanted to raise is that the Fermi paradox is not a very compelling reason to believe that there's no intelligent life in the universe. One can get around the Fermi paradox so many different ways where we don't identify the intelligent life. We have no proof of that intelligent life. That the fact that we have no evidence of intelligent life is a very poor argument for there not being intelligent life if all my double negatives didn't confound one another. Okay.
Do you mean, Ron, are you thinking of, for instance, where we could use the analogy that we might be observing a troop of chimpanzees or ants in an anthill or something, and we want to somehow make it so that they have no idea that we exist?
Well, I mean, I'm not even going to speculate on what the reason is. My point is there's lots of ways that we could be ignorant of intelligent life in the universe. And the fact that we haven't detected it yet is a poor reason to believe that there is no intelligent life in the universe. We simply don't know. There's many workarounds of.
Well, I mean, I wouldn't call this
paradox.
I wouldn't call this the reason that I explored this, because I've always been interested in the question. But one of the instigations of thinking this way was, in fact, a recent trend among people, and particularly people inside Foresight, people like Eric Drexler and Robin Hanson and a few others, to embrace this anti-Copernican heresy, to suggest that we think the answer is that Earth is super special. It's the first. Humans are the first. And I agree with you. I don't think there is a compelling reason to believe that. But we've nonetheless seen papers and arguments come out in the last few years from folks inside Foresight and here in the space group and other things, trying to make reasons why it's not so odd to say there is a case that humans could be first. Robin first started talking about this idea of the great filter, suggesting that the universe is actually young rather than old, and because it's young, we could very reasonably be at the beginning of intelligent life. And there is actually one semi-compelling argument for that, which is that we are at our sun is one of the earlier stars to have what's called high metallicity, larger concentrations of heavier elements within it. That the stars of the first 6 or 7 billion years of the life of the universe tended to be just hydrogen and helium and a few other things, not too much in the way of other materials. And so only recently have all these other elements been common, and since those were necessary for us, that quite possibly we're at the dawn of that. And that's an interesting argument, which makes a case for it, but I don't necessarily go for it. However, when I started thinking about this in this way, I felt that even regardless of that, the idea that if you understand that what we look at, the baryonic matter, the fusion in the stars, is such a tiny part of the available energy in the universe, to my mind, while you can't say that guarantees the action is somewhere else, it makes it extremely unlikely that the action is within this tiny fraction that we come from, that we can see. And so that's the point I really want to bring into the debate, so people will understand there is a whole lot else out there. And I'll bet that almost everything in the 50 or 75 cases in that book, with one or two exceptions, were analysis of stars and galaxies and light from stars and galaxies and civilizations that live on planets or started on planets around stars and galaxies. There are some of these hypotheses in that book have been categorized into categories. That's a redundant phrase, but they've been grouped into these categories, one of which is what's called the transcendence hypothesis, where you start like us, but you transcend to some level of physics we don't understand, and therefore we can't see you. My explanation today is a little bit in that group, although it doesn't fit it exactly. But almost all the answers to Fermi paradox I see are in that group. And so I'm trying to not just give a new answer, but open up a new category of answers.
Sure.
And that's interesting if it's right.
Yeah. And that would,
We only have 2 more minutes
Oh,
left,
sorry.
so I want to also see if perhaps Ben wants to have a question.
Hey everyone. Hey Brad. Yeah, quick question. So I'm building a company called LifeShip, and we're sending probes, 3 different probes to the moon over the next couple of years, and then we're on one that'll go out of the solar system, launching next year. And this has
How much
a
are tickets?
DNA seed bank. You
I'm
can add your
kidding.
DNA and store it for $99. So it's,
right.
it's meant to be a mass market affordable thing. And we have several thousand people on it already. And then we're also doing a cultural archive and a story from humanity as well. And so I guess one of the things I'm looking at including is a large language model messenger from humanity. And I guess my question is, if you were sending an interstellar probe, what would you put on the interstellar probe as humanity?
It's some Chuck Berry. That was on Voyager 1, of course, the famous Saturday Night Live sketch about it. So my thesis is, and this is not going to be the one you want to hear, but I think if there are intelligent beings out there, anywhere even remotely near here, that they are fully aware of us, that if they are interested in us, they are watching us. They could be, it's more likely they're just not interested in us, but if they are interested in us, they are watching us and they will decide. But if they want to download a large language model, they can get one from the internet. They don't need it from your probe, I'm afraid. And the same thing with what's on the Voyager plaque. The Voyager plaque was a nice, elegant, and romantic idea, but it's not actually related to what I think is likely to happen, unfortunately.
Well, we're
Totally.
at the
About
hour.
So I'm okay, and John hasn't, or Carol, or Carol, if you want to come in. John gave me some comments earlier, so.
Yeah, we're at the hour. I have to hop off, but I can leave this room open and make you host, Brad, if you want to stay on with people.
All right, sure, go ahead. I mean, I don't think we'll stay much longer, but since I have to go and spend another hour at the DMV wasting my time like I did yesterday.
Great. I'm glad we're not out of
Intelligent life.
yet.
Not in the California state government. All right, bye-bye, Allison. Thank you.
So
Go ahead.
regarding the waiting for colds, if we assume that you're limited by the speed of light, so you can't advance past that, like it's a hard limit, then there may be competition that is outside of your light cone that may enter your light cone at any moment. And if you are not spending all of your time preparing for this hypothetical attacker, then when they arrive, you may not be prepared. It feels like that would be a very good reason to not wait around for the cold, even if it's more efficient. I mean, this is basically a dollar today is worth more than a dollar tomorrow, right? You don't know what you're going to run into.
So I do cover that in the article, and I should have mentioned it. I guess I didn't put a slide about it. But when I mentioned that the one time you're not efficient would be war, this was actually me making a vague attempt to be slightly scientific, because if you're going to be scientific, you have to make a prediction. And my prediction was the only place we might see them would be if they come into conflict, because there they would emit energy that we would see. Because they're in war and they're not being efficient. They're more interested in blowing up their enemy if it comes to that. So what I predicted was, if we were ever to get a chance to see them, we should look for some sort of energy emissions in roughly a plane, because 2 spherically expanding spheres of control would intersect in a plane. And then again, that's assuming the speed of light is a limit. And if you start assuming that the speed of light is not a limit, well, obviously all of our physics gets undone. And so that's a bad thing. But most of these assumptions can break down if you're able to travel significantly faster than light. So yes, that's what you would look for. Now, would you spend all of your effort preparing for battle with the enemy? No, you wouldn't. We don't. We spend, NATO, you're supposed to spend 2% of your GDP.
I would say that us continuing to advance technology as fast as we possibly can, like that is something that humans do. Like we throw everything we have at moving forward. And
we don't throw everything. I think we throw maybe a few % of our resources at that.
I think we're very bad at it. I guess my argument here is that humans consume all the resources they can get their hands on, and they turn it into stuff. And that
mostly we turn it into more humans. Through all of history, all of life is just mostly turned it into more life.
Yes, we turn it into something other than its natural resources, even if there's letting it sit and maybe use it later more efficiently. Like we could do that. Like we could probably use oil more efficiently in 100 years, but we don't sit on oil. We burn it as fast as we can so we can turn it into other things that we think are useful today. And so I feel like I guess my instinct is that an alien civilization would want to do that. Even if they're not directly preparing for war, they are trying to advance themselves so that they are better prepared for whatever might come. Because you don't know what's outside your light cone. And so you don't know what the enemy is. And so the only option is to turn energy into information processing or research or whatever. It doesn't have to be weapons. It can just be something that makes you more advanced. So when you encounter whatever it is that's out there, you're more prepared.
Well, so I make this supposition, and this is not a proven supposition, that physics can be mostly completely understood, and that after some number of millennia, maybe even tens of millennia, all species that have a good level of intelligence, basically, okay, we have figured it out.
I see. Okay.
We can close the patent office because everything's been invented, which is obviously I don't think that ever happened. It's a story that goes around that was proposed. I mean, it might have been proposed. It wasn't seriously considered, but nonetheless, I'm suggesting that physics is finite, and even engineering is semi-finite. I mean, there's infinite variation in what you can do with engineering, but yeah, I mean, and in particular, if there are lots of civilizations that are coming into conflict, as you face civilizations, you'd either lose or win, and the winner would eventually learn that nobody's got better shit than us, or everyone's equal, and so you would be vigilant, you'd prepare. One of the things about expanding at the speed of light is you don't get any warning about meeting somebody, or very little warning. Although, actually, I shouldn't say that, because it depends how long a civilization takes. Like we humans, we've taken a few million years to get to the dawn of technology, and so everyone in this galaxy could have detected us, because you can send a space probe in the speed of light anywhere in this galaxy in 100,000 years, right? So if you become the kind of civilization that can send out von Neumann space probes, you've sent one everywhere in the galaxy in a very short amount of time, much shorter than the lifetime of the human race. So you would sort of know about those. I mean, you might be nipping them in the bud. I mean, I'm sure you've read The Dark Forest, which is not very good with its physics, but it's been put forward at least into the public vernacular. There's going to be a movie, of course, of it coming out. Is it coming out this year, I think?
TV series by Netflix, I believe.
Yeah, Netflix TV series. So those ideas will become sort of household language soon. But it's not out of the question that a civilization might decide, nip every competitor in the bud, and you could do that within some zone. You'll eventually reach someone you can't nip in the bud, though.
Right.
Especially if you go intergalactic. John, you had your hand up? No, you just exercising. You put your hands in the air like you just don't care. All right. Anybody else want to discuss more, or shall we close it up?
One other thing, if you don't mind.
Sure.
Hypothetically, could
you're
one
keeping me from the
also-
DMV, but that's
I'll try not to keep you too long from the DMV. I don't want you to miss out on that opportunity.
I spent an hour there, and they finally said we can't do anything for you because we take 24 hours to process your credit card. Amazon can process it in about 3 seconds, but the DMV takes 24 hours. Anyway, go on.
So, do you think it's reasonable that some alien civilization, their mechanism of discovery is they've searched all the places they can think to search, and their new mechanism is to basically just spin up new civilizations, let them evolve, and see what happens, just to see if they miss anything, like as a search strategy. And perhaps we are just part of their search strategy for new technology, just to see maybe we come up with something they didn't.
Well, unlikely that we'd be a search for new technology, but we could be a search for new culture and art and interesting. So we don't know anything about their motives and what they're interested in.
Sure.
So it could be anything like that. There is, in these books of answers to Fermi's paradox, there is always a section on this is a simulation. Not a word I like, but it is actually one of the more consistent answers, I've got to say, though, because once this is, I call it a synthetic universe rather than a simulated universe. It's obviously real by our definition of real. But once you go with that one, well, then there's no need to explain why the sky is empty. The sky is empty because that's what they programmed. Or the sky is a copy of the old sky. Actually, I'm sure you've heard that Elon Musk has said he supports the simulation hypothesis. Maybe you've heard that. And I have not had the chance to say this to him because he doesn't chat with me very often for some reason. But the argument is, if this is a simulation, then we are already a multi-planet species. In fact, we're a 100,000 planet species, virtual planet, and Mars isn't even on. Right? They're only simulating a few square kilometers of Mars where the probes are. So, devoting your life to making Earth a multiplanetary species, humans a multiplanetary species, and going to Mars, you wouldn't do that if you actually believed this was a
Right.
if
If it's simulation,
if this was a simulation.
right? If it's simulation, you just load the last save if it ends early.
Well, I mean, it's just there's not the whole simulation hypothesis is that there's an arbitrary number of them, and so therefore, in fact, that is the proof for the simulation hypothesis that I guess that would Nick Bostrom put forward. And so anyway, so by definition, your proof contains the axiom that there's a million of other ones like us.
Yep.
And so therefore you don't need to save the Earth by going to Mars. Anyway, but could we be that? We could be. That is a consistent answer. I've got to admit, it's not an answer that a lot of people are satisfied with.
Sure.
Right. We don't want to just be someone's science experiment. But the way I express this, in fact, I say, basically the simulation hypothesis is actually the same as religion in that the universe has a creator, but that creator is a grad student doing a term project, and her name is Martha. And so that's God. God is Martha, and don't piss her off.
Overall, I like your hypothesis here. I think the only thing that makes me unwilling to fully adopt it is just I feel like we don't understand dark matter well enough to. It makes me hesitant anytime someone tries to build on top of dark matter. Like, we think it's out there. Like, we have so little information. And it doesn't mean you're wrong, of course. It just means that it's building on very shaky ground, from my point of view. But so we don't have a lot of strong ground to build on. So sometimes you just have to build on shaky ground.
Well, I was actually wary of the same thing, and that's why I limited to saying some things that are extremely likely to be true about dark matter, even though we know nothing about dark matter. And one is our model does demand that all particles have an antiparticle. Right? If dark matter particles don't have an antiparticle, then they're even more outside our physics than is being suggested for them. And also that they can be turned into energy through the event horizon of a black hole is what Adam hypothesized. That again, if that's not true, then that's saying that dark matter is even weirder. And so I think trying to say that the basic concepts that we're accepting in our physics apply to it. Other than that, and we also know by definition, dark matter can be managed with gravity. Right? It does respond to gravity. So it is possible to collect it. Not easy, but it's possible. So I'm not trying. I don't want to suppose anything more about it than these very basic things.
Yeah. It still requires, though, that dark matter is the answer and not a different definition of gravity.
Well, yes. So if dark matter doesn't exist, although these galaxies that don't seem to have dark matter open up interesting questions.
That was very interesting. I hadn't heard of that before.
Yeah. It's not a lot of them, but they don't lens the way their mass the way they lens suggests their mass matches what we see.
It's fascinating. So I did not know that, and that definitely puts a big dent in the just different definition of gravity theory, or whatever it's called.
However, even if the dark matter thesis is wrong, it remains true that baryonic matter or hydrogen fusion is a very inefficient way to turn matter into thought. It's just not. The dark matter says that even the baryonic matter is just a small part of the matter. The stars are still a small part of the hydrogen, and the energy we get from the stars is a small part of the energy in them. So you can actually remove dark matter from this. In fact, the reason that I made this about dark matter was when I started just thinking about, someone said, well, if there are aliens out there, we can't see them. And I said, you mean it's almost as though we can't see most of the universe? And I said that as a joke, right? Because everyone says, oh, right, we can see most of the universe, at least if you accept the dark matter thesis. And so that's why I started with the dark matter hypothesis. So
that's
all righty.
Maybe dark matter is just
my first thesis, which turned out to be wrong, was that it was the aliens who had, multi-billion-year-old aliens who had actually created the dark matter. Are you there?
What was wrong? What was wrong about it?
So the evidence suggests dark matter was present in the early universe.
I see. Okay.
It's not, dark matter is not artificial. I thought it would be quite interesting if you could hypothesize that it was artificial, but that seems unlikely.
Yeah. Okay.
All right. Thanks very much. We'll see you all next time.